We are ready.
Good, okay, so you're recording?
Yep.
Good. Hamid says hi, by the way. He would have loved to be here, but he has a work meeting. Okay, thanks everybody for taking the time. Coming from far and wide and far. Anshu's going to be here in a minute, so I suggest that we start, and we also have things recorded. It's great to see everybody here for Daniel Lejeune's PhD defense. He is also coming either far or wide, one of the two. Both, I guess. And he's going to be presenting his PhD work today. We can have lots of time to interrupt Daniel since a bunch of us are here in person. I will monitor the chat if you want to put in a chat question, but also, especially committee members, if you're remote, just speak up and we can interrupt the proceedings, at any point. It's better to get things clarified right away. And then after the presentation, we'll have lots more time for questions. So without further ado, take it away.
Thank you, Rich.
And you need to really project in this room.
Yes,
Those people might want to move.
definitely move close because I am a quiet person. Okay. So thank you all for being here. And my wife and parents will be here, but they had a little bit of trouble finding Duncan Hall from the Greenbrier lot. So,
Oh, indeed.
yeah. So I'm going to talk to you about regularization with randomization in linear ensembles today. But
Triple check that your committee can hear you. Okay.
can my committee hear me okay?
Yes.
Okay,
Good.
great.
Yes.
Also happy to see that my wife and parents have arrived. So glad that they were able to be here. And that they found Duncan Hall and the room. Okay, so before I talk about randomization, I want to tell you a little bit about my PhD journey. So I started at Rice in 2017. During this time, I got married, which was nice. I also spent a winter. Well, I have a little bit of an echo. Okay, it's all good. A winter at TUM in Munich, Germany, which was very lovely. I've also my hair has gone on a journey during my PhD, as some of you remember. And mostly it has gone. That's the journey it's been on. But now if I want to do Halloween costumes, my wife makes me wear a wig. So you win some, you lose some. I've also gone on a medical journey during my PhD. I've had 2 surgeries for appendicitis and melanoma. Fortunately, both of these were successful, and so I'm all good.
Is that actually you in the left?
This is
On the left.
That's a stock photo from Google Images. So you probably are more interested in my research journey. So early on, we did a lot of work with randomization, which you'll see as a recurring theme today. So we did some early work using a count sketch to do machine learning on sparse data in billions of dimensions. I did a couple of works using multi-arm bandits, where first of all, I did approximate k-nearest neighbors by only sampling some of the coordinates and using these heap data structures. I did level set thresholding on graphs using a bandit algorithm. Then I decided bandits weren't that interesting anymore and got into what's going to be part of this talk today. This mini patch learning or subsampled data set stuff, but I'll talk about that later. And then we've also did some empirical work on that with Tianyi from Ginevra's group. I've done some compressed sensing, leveraging the Poisson nature of a particular problem to really crank down the number of measurements you need using only a single sensor. I've done some work on adaptive dropout, showing how adaptive sampling in popular methods for sparsity actually correspond to well-known classical sparsity-inducing penalties. I'm really excited about this work that I did with Reinhard and Jiayu at TUM, where we are looking at under what conditions, necessary and sufficient conditions, that performance is preserved under distribution shifts, covariate shift. And what we're going to talk about mostly today is asymptotics of the sketch pseudo inverse. We also just put this on archive. And this is close work with Pratik from Brian Tibshirani's group at CMU, but now Berkeley. Yes, Rich.
Given that you're an expert in Poisson processes,
Okay.
would you say that this is your publication journey is a Poisson process?
I would not, and because 2020 is a bit of an anomaly for obvious reasons. One, the pandemic, but it was also around the time that I met my wife, so you know. I had a couple of honorable mentions, some very large group collaborations and signal processing, and a couple of papers that are on archive only at the moment, but we hope that they'll make it out soon.
So sad you're not talking about only rugosity today.
Yeah, I know. Okay, so now I'm going to get to the actual talk. So, okay, you are a data scientist, and you get a data set, and you say, "Man, I'm going to make a lot of money off of this data." So you start looking at it, and it's a bunch of medical records. You have a bunch of features, age, lab results, and so forth for many different instances. And you say, well, maybe I can make a predictor that will tell what are the odds of that this person will have cancer in the next 5 years. If I have this, I can sell this to hospitals. It'll be great for the world, and it'll be great for my wallet. But you start looking at the problem, and you realize maybe there are millions of instances that you have, which is going to be expensive to compute. And maybe there's tons of features as well. And so now between features and instances, you have some cubic combination of computational time. And not only is there a computational problem, but there is also a statistical problem in terms of the curse of dimensionality. There are too many possible solutions for you to know what is the right one. And it's a classic machine learning dilemma. And so a machine learning data scientist person says, I'm going to apply Occam's razor. Probably the answer to this question is not that complicated. And so the way that I'm going to realize this to address all of my issues is I'm going to take subsets of the instances, and each subset of the instances, I'm going to only take subsets of the features as well. And I'll train a model on that. And I'll make another random subset and another random subset, and so on and so forth. And the advantage of this is that it solves, like I said, all of my computational problems because I have few instances and few features. And it also is going to be effectively a simple model because now it's just an aggregation of fairly simple models. So in some sense, this is much simpler than the space of all possible functions that could fit to my features. And so I do this, and I sell this to the doctors, and then the astronauts say they have some problem, and I do the same thing for them. And the fire department says they have a problem, I do the same thing for them. And the scientists say they have a problem, and I do the same thing for them. And they're all happy with their data-driven results, and I'm happy with how much money I made. But then I say, well, what am I actually giving these people? Like if I was doing a model trained on all the data, you know, I know linear regression, I know what it's doing, but if I'm doing all of these subsets, what is the aggregate? And so why am I interested in this question? Because this is actually a real problem. So one of the best performing off-the-shelf methods is random forest, and it essentially works off the same principle. Each decision tree is trained on some random sample using bootstrap sampling of the instances, and at each branch you use a random subset of the features. So similar in principle. People also do random projection ensembles, where again they randomly project or use a random subset of observations, and they also will compute some random projection of the features. You know, in this day and age, I won't talk anything about this beyond this slide, but I mean, neural networks are basically just subsequent layers of random projections. And so I think understanding random projections or random subsampling and its effects are a very important, like, foundational problem. So prior work has considered this to an extent, usually concerned about what performance do ensembles, which are just collections of these randomized predictors provably achieve. But it's actually difficult to analyze these things directly. In fact, I don't know of any analysis that really captures true random forests. They usually have to be simplified in order to give results. And usually the results that people prove are that they are consistent in the sense that if you have sufficiently many instances, you do converge to target function. And we also know things like, because of variance reduction, combining many of these predictors is better than just having one of them. But I want to ask a different type of question, which is not, are they good if you have many samples, but what do they converge to in this limited sample regime? What predictions are they actually making? And the same question as our data scientist wants to know. And so people have shown that there's some implicit regularization in when you do subsampling like this. They actually can be better than if you had just used the full data. And so if that is the case, can we make this explicit? I borrowed this terminology from Ginevra. And the reason why I really like this type of result is that it's stronger than just consistency or like some risk upper bounds, because not only do we understand how well they perform whenever they are optimal, but even whenever they are suboptimal or they just do something else, we know exactly what that something else is. So just to set up a little bit of notation, we'll have a ground truth function f and I have a bunch of estimators. We're interested in squared error risk today. And so this is just a squared error of the ensemble. So you see the sum 1 over k compared to f. And this is going to be an expectation over possible training instances or test instances rather. So in the early work that I did, I considered the following model. Let's say we have training data, x1 through xn, and y1 through yn are the labels. And we're going to assume a Gaussian isotropic data model on x, and we'll have some ground truth coefficients that have unit norm, and we'll have an additive label model for the training data. What we're going to do is construct estimators of the following form, which looks a bit complicated, but these S and T matrices are subsampling operators, which are described as follows. So we'll have subsampling operators S, K, and TK for each of the K members of the ensemble. We have M greater than Q plus 1. This means that we'll have Q features, effective features, that we're going to subsample with S. We'll have M observations that we're going to subsample with T. And we need M greater than Q. That basically means the subsample matrices need to be tall because we're going to do ordinary least squares and we want a unique solution. So subsampling looks like this. T samples rows. These are the red bars. S samples columns of the data matrix or the features, giving you the green, and the resulting subset of the data is the blue patches. And we're going to do this multiple times. Yes, Rich.
Is this, on the left, is this the Lejeune tartan?
Something like that. Yes.
You probably wish I was on Zoom and not in person.
I'm glad to have you here, Rich. Okay. So I'll just do this many times using an independent subsampling for each member of the ensemble. And so what we did then was we just computed what is the form of the risk, the expected risk. And we just used the fact that these are Weishart matrices and used some fancy conditional expectation. And you turn the crank and eventually we got a couple of theorems, which looked something like this. So if we had an asymptotically large dimensionality converging to fixed aspect ratios, then we had a term for the risk of an ensemble of finite size or finite many members, K members. And you can see that the aspect ratio of the subsampling ratios, alpha is the subsampling ratio of features, and eta is the subsampling ratio of observations. And so since the eta only appears in the second term, when we have an infinitely large ensemble and K goes to infinity, the second term vanishes. So for the infinite ensemble, if my clicker will work, if infinite ensemble, in fact, because we made these subsampling matrices such that our resulting matrices were tall, it only depends on the feature subsampling alpha. So then we said, okay, we have an expression for risk. Let's just optimize it. And it's going to turn out to be equivalent to ridge regression. So just as a reminder, ridge regression is we just saying we're going to have a ridge penalty lambda on the least squares loss function. And so then if we tune alpha, we actually will get the same risk as if we had tuned lambda in the ridge regression. So whatever was the optimal ridge regression, its risk can be achieved by an infinitely sized ensemble with no regularization whatsoever. So somehow we're getting implicit regularization due to subsampling. However, the problem with this proof is since all we did was turn a crank with Y-short matrices, we didn't really shed much insight as to how this is actually happening. Literally all we did was we took the expression for a risk for ridge regression, and we optimized the risk for subsampled ensembles, and they were just mathematically happened to be the same thing. And at the time it was interesting, but it didn't feel much more like a mathematical, much more than a mathematical curiosity. So, but we said, okay, ridge regression is optimal, so the ensemble can also be optimal. That's nice. But does this actually mean that we're converging to the same thing as ridge regression? Maybe. For infinite dimensions, we know the MMSE is unique, so probably true in infinite dimensions, but we didn't like how not rigorous this argument seemed to be. And still, I'm not sure it really answered the question of our data scientist of what is this predictor, especially for, say, for finite ensembles. So around the same time, there was a similar observation made, and it helps to reformulate our problem. If, say, we only did feature subsampling, then our ensemble will have the form on the right-hand side, where you see that the sum over K for an infinite ensemble just has a bunch of these S sub K terms. Well, another group investigated the determinantal point process, which is another subsampling operator that I can't explain, but they proved that over all possible subsampling operators, if you take the expectation over that distribution, they actually obtained an expression in terms of a ridge regularized version of the original matrix M. But if you notice, this is actually more or less the same form as we had in our ensemble for our subsampling operators. So they provided this equation for how to determine lambda given your determinantal point process size. It's just that we said, okay, there's something more here. And it looks like someone else was able to show that there's some equivalence to ridge for this other process. Maybe we can show something better for our process, which is a bit more commonly accessible. Like it's hard to actually sample determinant point process.
So I have a question. So, but isn't like that result independent of the Gaussian assumption on X?
True. Very good point. So this M is pretty much any positive definite matrix.
But in your case, don't you need to assume Gaussianity of the inputs?
Yes, another problem. In fact, that's my first problem with this result.
Oh, sorry, okay.
So I didn't like how we had to assume isotropic Gaussianity on X at all, because it seems very restrictive. So it turns out you do need some kind of isotropicness. In fact, like a determinant of work process has this implicitly, even though it's not obvious. So our solution to this is we're going to move the rotational invariance from the data into the subsampling operator. So we're going to, instead of subsampling, we're going to use sketching matrices, which are drawn IID Gaussian, or IID from some distribution, doesn't have to be Gaussian. That's where we're going to start. Another problem is we only had marginal error results over the distribution because we only had like risk, expected risk. So we can get single instance results using random matrix theory, which is what we will do. Another problem is we only were able to use ordinary least squares with tall matrices. We would like to be able to study this over parameterized machine learning regime. So we want wide matrices, and maybe we're going to do arbitrary ridge regression instead of ordinary least squares. So we're going to fix all of these problems. And the way that we're going to do that is using this tool. this formalism of asymptotic equivalences of matrices. And so if we have a sequence of matrices A and B, we'll say that they are asymptotically equivalent, so they are increasing in dimension. If for any sequence of theta n, the inner product between theta and the difference of A and B converges to 0. So usually the way that this is used is A will be some random matrix and B will be some deterministic matrix. We can say that this random matrix is equivalent to this deterministic matrix in this first order sense. If we have this type of equivalence, we can use this calculus to add them together or multiply them. We know that their elements will actually converge, even though they aren't the same matrix in finite dimensions. And we can even differentiate them with respect to scalar variables. So we're going to use an existing result from random matrix theory to prove our result. And just to give you a quick interpretation of what this looks like. So what this says is if you have a sample covariance matrix, so if we look at equation 32 here, I meant to remove these numbers, but I guess it's useful now. You have a sample covariance matrix, and in general, I'm going to use complex matrices, so that's why I have a Hermitian transpose with an H there. A sample covariance matrix inverse inside this this minus Zi inverse. This is called a matrix resolvent using the resolvent formalism. So this resolvent is going to be asymptotically equivalent to the resolvent of the population covariance matrix scaled by some constant C, which is a function of Z. So whatever Z you plug in, you'll have some fixed Z that this converges to. And that is related by this equation. So this is usually proved for complex Z. And so if Z is in the positive complex semiplane, then C will be in the negative complex semiplane. And it's always a unique solution to this equation in that plane. But this is actually a problem because we are going to be interested in, I mean, if you look at this, this is essentially the ridge regularized inverse that we're going to use in ridge regression. So we need real arguments to be able to study ridge regression, which is actually a bit problematic because the uniqueness of the solution no longer holds whenever this is a real argument. So this is something that we fix in our results to start off. We perform an analytic continuation of this result to the real line. And in doing so, we identify the bounds for which the solution is unique. Basically, if you're on the other side of that, there could be tons of solutions, but as long as you're on the correct side, you get the solution that you want, essentially, the one that is the analytic continuation of the complex solution. So in doing so, we actually identify, I won't talk about this much today, but we identify the limits of allowed negative regularization in ridge regression, which we think is independently interesting. We've also identified a way to compute the smallest non-zero eigenvalue of a sample covariance matrix, which we don't think has been proven anywhere else before, which also we think is of independent interest. But more towards our point of sketching, we have reparameterized things slightly, multiplying by Z on both sides and reparameterizing C into this zeta variable. And in doing so, we have things that we don't have to worry about problems at Z equals 0 because now everything is well controlled. And we're going to use this to prove our following result. Also, this maybe is of interest to people. Well, what is this zeta? I don't like solving this implicit equation. Well, actually, we can say that zeta can be written in closed form in terms of the sample covariance matrix, if that's of interest to you. But we're not going to focus on those details today. So starting from this equivalence, where we have the Z and the zeta multiplied by each other, it's surprisingly simple to obtain the sketching equivalence that we consider to be our primary result. So we're going to reparameterize a little bit. So remember our subsampling matrix S, well, now it's a sketching matrix, and we're interested in what happens if we sketch a positive semi-definite matrix A. So we're going to rewrite X in terms of S and A, and we're just going to take the negatives of Z and zeta and call them now lambda and mu. Apply some Woodbury magic, and now we almost have the form that we want. We can apply a uniform convergence argument to get rid of these A halves, and now we have a what we call the sketch pseudo inverse, because if lambda was 0 and S was a subsampling operator or orthogonal in general, then this would be a pseudo inverse of S transpose AS. But this is the same form that we wanted to be able to study in our subsampling case. And now we can study it. Now we know, we're going to know a lot about it for sketching. So our equivalence looks like this. The sketch pseudo inverse with regularization lambda is equivalent to the ridge regularized inverse of A itself without sketching with a new regularization mu. Mu in general is not the same as lambda. And it's given by this equation, and we have the proper bounds. So, but in other words, sketching and then doing a ridge regularized inverse is equivalent to doing some other ridge without sketching. And now our data scientist is happy. He finally knows what's going on when he does sketch ridge regression. Well, maybe. We're going to get to that in a bit. Additionally, whenever lambda equals 0 and the sketch size is sufficiently small, this actually coincides precisely with the result from the determinantal point process. So what does this look like? Well, if you recall, I said that if you have an asymptotic equivalence of two matrices, then that means their elements converge. So let's just pick some A. We're going to pick A that has equal, it's going to be diagonal. It's going to have zeros, ones, and twos along the diagonal. And we'll pick subsampling ratio of our sketch size. So it's going to be 80% of the original dimension will be our sketch size. We're going to use regularization strength of 1, and we're going to have an induced regularization in our equivalence of about 1.63 if you actually compute it. And so what I'm plotting on the left is the convergence for different values of P. As we increase the dimensionality of this matrix, we converge more and more closely to 1 over A plus mu, where A is one of the diagonal elements of A. That's what we converge to along the diagonal, and the off diagonals all converge to 0, just as we would expect, because the inverse of a diagonal matrix is also diagonal, right? So things converge element-wise, just like we expect them to. I think it's helpful to make an analogy, and it's just an analogy. It's not technically the same, but it's an analogy, an analogy to blurring. So say we start with an image and we downsample it. So this is like sketching. We're going to downsample it to various different sizes. This is like using different sizes of a sketch, smaller and smaller. We're going to do a ridge regularized inverse. So we're going to blur it. Okay. If we blur the downsampled image, and then we bring it back up to the original dimension by unsketching it, or upsampling in the image case, then you actually find that the smaller you made the matrix before, the smaller you made the image before you blurred it, the more that corresponds to using a higher blur amount in on the original image. And so this is going to correspond exactly to the relationship between lambda and mu in the induced regularization, and also and the subsampling ratio alpha. So what does that look like? So here's a toy example where we're going to have A that has eigenvalues of 1 for half of them and 0 for the other half. And this R is a shorthand for the relative rank. So it's the rank divided by the dimensionality. So lambda to mu is always increasing and concave. Concavity is sort of just curious. I don't know how relevant that is, but increasing is definitely what you would want and expect. If you do more regularization in sketching, you're going to get more regularization out. Alpha to mu, the sketch size. So the smaller the sketch you use, the more effective regularization that you have. Unless you're in this weird regime that I'm not going to talk about much today, where you had a sketch size larger than your rank and you use negative regularization. We're not going to talk about regularization today, though. It's not that interesting.
Daniel, can I ask oh,
yes.
Sorry, can I ask a quick question? This is really interesting. And I want to ask, how does this equivalence relating kind of the sketch size here relate to your previous chapter in your thesis, your previous talk, when you're actually doing subsampling and your analysis from there? Do you actually get the same equivalence of regularization and the same kind of size Sorry.
Okay,
Yeah.
yes, so it's important to um, emphasize here that that was only in the lambda equals 0 case. And the reason why I say that is, as we'll talk about later, there are many different kinds, we suspect rather, that there are many different types of sketching matrices that you could use. And I think subsampling is similar to this, that actually are going to have different relationships between lambda and mu, but they all perform exactly the same when lambda is 0. So the determinantal point process and the subsampling, I don't think would actually do the same for, well, I don't know about DPP, but subsampling definitely does not do the same as this for general ridge regression. It only does the same when lambda equals 0, if that makes sense. It may not be clear why. I can try to give a better answer for that later.
Okay. Yeah. Yeah. But this is helpful, kind of pointing me in the right
Yeah.
direction. Thank you.
Yeah. Okay. So some other things that we know, and as long as we're in this nice regime and not in the weird one, mu will also always be greater than or equal to lambda. So sketching gives you more regularization. You're never going to get less if you have sketched. Additionally, there are some upper bounds. It's never going to be that much, but the upper bound is this 1 over q. So remember, alpha equals q over p. So this upper bound increases with alpha as well. And this upper bound is tight. So if either alpha is small or lambda is large, then you're basically at your upper bound. Oh, by the way, this plot here is, these are the same plot in both cases. I just rotated 90 degrees. So one is a function of alpha and the other is a function of lambda. So if the sketch size is larger than the rank, then if you have negative or positive regularization, you'll have negative or positive, respectively, regularization out. And if your sketch size is smaller than the rank, you will always have positive regularization. If you don't have this nice isotropic matrix that you're sketching, say you have something that's real data, like a Marchenko-Pasteur distribution, well, it's basically the same as you could see from these plots, except that unfriendly regime just sort of disappears because you can't have negative regularization if your eigenvalues are very small. That's basically the reason why. So I don't think that regime is very interesting. I think we have a question. Maybe? No? Okay. So unfortunately, the first order equivalence is actually not the end of the story. First order equivalence is similar to saying that we have expectation equivalence of two random variables. So just because expectation of y equals expectation of x, that doesn't mean that, say, we take higher order moments, that they are equivalent. So similarly, we can't compose, say, products of equivalence and expect just to be able to plug in the equivalences if they were not independent. The solution to this is we can actually, because of the resolvent form of these terms, we can take the derivative with respect to this scalar argument using the differentiability property of the asymptotic equivalence to get something that's second order. And that gives us something like this. This probably looks pretty complicated, but you'll see that we'll have some matrix psi in the middle of two of our regular sketch pseudo inverses. On the right-hand side, we get two of our equivalences with psi in the middle, but now we also have this mu prime. So mu prime is what we refer to as an inflation factor, and it's kind of like the variance of a random variable. So, second moment is equal to a mean squared plus the variance. Same thing here. There really are a lot of similarities between equivalences and moments of random variables. But the inflation factor depends actually quite significantly on this psi with respect to which this equivalence needs to be computed. And I'll show you what effect that can have right now. So we're going to use our isotropic rank half A again. And if we compute our second order equivalence with some psi that is the identity. So it has eigenvalues of 1 everywhere, including that all the places where A had eigenvalues of 0. So the key takeaway from this plot is that basically anywhere in the parameterization of possible equivalent mu's and possible subsampling sketch sizes, the inflation factor never vanishes. And this is because we're asking like equivalence in dimensions that are never seen by A, essentially. But if psi is equal to A, or in general, if psi is in the range of A, then there is this miraculous regime. Like this is really surprising to me, where if our sketch size is greater than, see here, 0.5, it's greater than the rank, then uniquely, only in the case where we aren't using any regularization, you see if we move outside on the mu, we start to have inflation again. But just in that one place where mu and lambda are equal to 0, there is no inflation factor at all. And so this, I think, coincides really nicely with classical results in sketching for least squares. They usually do least squares and not ridge regression, where they say if your sketch is larger than the rank, then you perfectly get the same result as if you had otherwise. Surprisingly to me, this doesn't extend to ridge regression in general, only to ridgeless regression, as it were. But I think this is ideal for this benign overfitting regime that's very popular in machine learning these days, where we say, oh, well, we want to apply zero regularization anyway. So as long as we are sketching in these problems sufficiently large, but still maybe to where we're reducing dimension, then we're in a friendly regime. And I'll show an example of that later. Because our data scientist wants to know, well, that's fine. This is sketching in the abstract sense. I want to know about machine learning because I'm doing data science and making money doing data science. So let's apply this to ridge regression. We're going to do a similar form as we did in the subsampling case at the beginning of the talk. We're going to use just sketching instead of subsampling operators. So these losses are identical to what I showed before, but we just have 3 different regimes. One where we do only observation side sketching, one where we do only feature side sketching, which we call dual sketching, and then we do joint sketching where we do both. Okay, so we can write all of these into this nice compact form, this X double dagger, where X double dagger changes depending on the regime. And then applying our equivalence once in the case of primal and dual and twice in the case of primal dual, we actually find that in all these cases, the regularized pseudo inverse of the data matrix itself is equivalent to, in the first order sense, to the ridge regularized inverse or pseudo inverse of the matrix. And in primal and dual cases, we have nearly identical relations between mu and lambda. They only depend, unsurprisingly, on the relevant sketch sizes. So if M is the sketch size for observations or Q is the sketch size for dual, that's the only thing that's different between these relations. And there's a more complicated version for the joint sketching, which reduces, in a simple case, to something that I think you'll find interesting. So this is the joint sketching, where we have as a function of both alpha and eta, so subsampling on both sides. And it's not that interesting if lambda is large, but if you go to lambda very small, say near 0, like we considered in the beginning of the talk where we did ordinary least squares, well, what did we say there? Well, we said if our subsampling matrices were tall, then it only depends on the feature subsampling ratio. In fact, we see that the same thing is true here. If lambda goes towards 0, I'm sorry, each row of this is a different like data aspect ratio, which is why these slopes go differently for like what's this phase transition boundary. But it only depends on alpha in the same regime. In fact, the converse is also true in the opposite regime where everything is wide, it only will depend on eta. So what does this mean? We have a first order equivalence of ridge regression. Well, in fact, it means that if we take any test point, which I'm calling W here, and any function, so any kind of prediction that we want to make on W, using our sketched version of beta versus beta hat ridge, the equivalent ridge, we make asymptotically the same prediction as the equivalent ridge for any single test point. My data scientist doesn't really like this qualifier. Why'd you say any single test point? I want to know what I do for everything. Well, we have to bring back in our second order equivalence because pointwise convergence does not imply uniform convergence. So, but we can do that very easily. We're going to use similar notation to before. We have a psi matrix again, but we're going to define a quadratic error matrix, error metric for our ensemble. Well, for any beta and beta prime, but we're going to be considering an ensemble again of size k. And this error metric is just a distance defined with respect to some positive semi-definite matrix psi. And this includes, for example, test risk. So we get another equivalence. In this form, it's not as friendly to interpret, so I'll just write it this way instead. So basically, the distance between our ensemble and any reference beta prime, such as the ground truth beta star, is going to converge to the distance from the ridge solution and that beta prime plus some inflation. So essentially, no matter where you are, you're always farther than the ridge solution. Unless you let your ensemble size go to infinity, then you're going to be exactly ridge. And in that case, our data scientist is very happy. If we have a finite k, in some sense, you are always worse than ridge because you're always further than whatever than the ridge is for whatever reference beta that you're interested in. This is true unless you're in that miraculous regime where we have sufficiently large sketch size and psi is in the range of A, and we have no regularization. So what does that look like? Let's do an example. Let's see how good ensembles of sketch predictors are we're going to give a fixed computational budget. So we're going to assume that like P is smaller than N, so solving the least squares problem has order P squared N computation. And for ensembles, we're going to say, well, we're going to use a sketch size of alpha, which decreases that P to a Q. And so we can use an ensemble of size K equals 1 over alpha squared in order to have the same total computation. And we're going to use an isotropic data population covariance matrix. We're going to sample data from that, and then we're going to sketch that data. So like our A in this case has a Marchenko-Pastor distribution. What we're going to do is we're going to fix several target regularizations. And then for that target regularization, we're going to choose different choices of alpha, and then lambda will be uniquely determined. What we're going to plot is the relative error, which is how close we are to the ridge solution, which is the one we desire because we fixed some target mu d. And we're only doing dual sketching, by the way. And we're just going to divide that by the norm of the ridge solution. So if this is near 1, then we're doing a really bad job of approximating the ridge regression solution. So if we do this in 2 different regimes, one, say, estimation error, so trying to estimate the ground truth coefficients, it doesn't really make sense to do this because our data covariance doesn't even cover all of the dimensions. So it's no surprise that we actually do a really poor job. We have a non-vanishing estimation error. And in fact, it doesn't even matter for this fixed computation. It doesn't matter what our sketch size is or how many members we have in our ensemble. We're never really going to beat roughly constant error. So estimation error is pretty much impossible in this regime for a fixed computational budget. You could do better, assuming you had some small eigenvalues in sigma. If you had significantly large computational budget and you could actually let K go to infinity for some constant sketch size. But that's not the regime that we're talking about in this experiment. On the other hand, say we're interested in prediction error, in which case psi is just equal to sigma. So this is our test risk. In this case, we again have non-vanishing prediction error for non-zero values of mu, but as mu gets closer and closer to 0, then what we find is the relative error also goes to 0. So uniquely, In the prediction error case, if we have no regularization, we are converging to the same predictor as the ridgeless regression predictor with lambda equals 0 or mu equals 0. And in fact, in this case, we don't even need the ensemble because even with k equals 1, we're going to converge to it anyway. So for a fixed computational budget, I think it's safe to say that ensembles are actually not efficient. But if you have parallelism at your disposal, you can save significantly on time. So this is not to say that they're useless, but it's just to say you're probably not going to save on, say, energy by solving problems in this one.
The minor question.
Yes.
Why is there an easy explanation for the blips that go up?
Oh, yeah. The
Red
blips,
arrow
these
is-
are integer errors. So I have a floor here.
Okay.
So every time you get to a different
Yeah.
integer. But those don't really help you at all, right? Okay, so Anshu would say that in practice, I'm never going to use an IID Gaussian sketch, Daniel. So what about something real like count sketch or fast Johnson-Lindenstrahl sketch? So this is where we propose a conjecture. We say, suppose we have some norm preserving sketch. So we always use a norm preserving sketch. If you sketch, you still have the same norm in and out. Such that S is asymptotically free, which I cannot explain here, but it basically means rotationally invariant. This is a notion from free probability theory. So suppose that S and A are asymptotically free, then we should always have the similar form of our equivalence. So this is a conjecture. We just suppose that this is true. This does include IID sketching as a special case, but it also includes, importantly, orthogonal sketching. And so this is Ginevra, where we're getting back to your question. This relationship between lambda and gamma is going to depend on the spectrum of the sketch itself. So subsampling is always going to have an isotropic spectrum on S, whereas IID sketching has a Marchenko-Pasteur spectrum, so you're not going to get the same relation. However, they coincide at lambda equals 0. But what about other efficient sketches like count sketch, fast Johnson-Lindenstrahl sketch, that only take like n log n time to compute rather than n times p? And also orthogonal sketching, which doesn't lose as much information. What can we say about that? Well, in fact, oh, by the way, and also the second order sketch and whatnot, these naturally follow because all you have to do is apply a derivative. If you have the relationship between lambda and gamma, you're good to go. So orthogonal sketching. Well, assuming the previous conjecture is true, we prove the following conjecture, where if Q actually has, so Q is taking the place of S, but I'm using a different letter because it's an orthogonal sketch now rather than some IID sketch, then we actually obtain what is the relation between gamma and lambda. And in fact, gamma is always less than the mu from the IID sketch. So orthogonal sketching gives you less of this distortion, if you want to call it distortion, or less of this effective regularization due to sketching, which may be desirable in cases where you really want to use whatever you are applying. So same form as the IID, but with less regularization. And so we did a bunch of experiments on a bunch of practical, commonly used sketches, just to see how they match up with these two equivalences. So the black dotted line is the same one I showed before at the, about a third of the way through the talk. We're just looking at the diagonal elements of this sketch pseudo inverse. But the red lines are the equivalents for 1 over A plus gamma, where gamma is the equivalent regularization for the orthogonal sketch that we just proved. So the orthogonal matches that very closely. Count sketch, Anshu's favorite, is actually very similar to an IID type of sketch. We can ignore adaptive sketch, and I can talk about it later. If you're interested, it's very different. Fast Johnson-Lindenstrahl sketch, which is like an orthogonal transformation followed by a sparse IID sketch, is unsurprisingly, I think, similar to IID, although it's a little bit worse. And worse in the sense of it has even more regularization, which is why it's further to the left. One that I think is really interesting is a fast subsampled randomized Hadamard transform, which is like, essentially you do like a sort of like a permutation and then you do fast Fourier transform, and then you subsample some columns. If your dimensionality is a power of 2, it's exactly like an orthogonal sketch. But if you're not a power of 2, like say you're 1 or 2 larger than a power of 2, so I use some examples that are just power of 2 plus some small number, then it's very different. And the problem is the way that people say, they always say in the paper, without loss of generality, we'll just zero pad and it'll be fine. But in fact, it's not. So I found this to be very interesting. And I think that, I hope rather that it should be possible to prove that all of these operators are in fact asymptotically free. And then if you know what their spectra are, then you can determine this mapping. I also think that this in general is a better, more principled way of comparing sketches. I mean, obviously you can compare them in terms of efficiency, computational speed, but this is more of a way of comparing what they are actually doing. So hopefully this is useful to the community in that regard. So to summarize, in early works, we showed there are hints of a deep connection between sketched ensembles or subsample ensembles and ridge, or using these random projections, in the sense that if we tune them, we could get the same risk as optimal ridge regression. But what if things were not optimal? Well, the current work that I just showed shows that there's an asymptotic equivalence between random projections, like of the ID kind, and ridge, in a very precise sense. And there's some sense in which we are equivalent to ridge on a weak level, even for single learners. This is the first order equivalence. But if we have an ensemble, then we converge in pretty much any quadratic metric for the ensemble. And if the sketch size is sufficiently large, this incredible regime, then even with only one member, we're going to converge very precisely to ridgeless regression, even if we don't have an ensemble. So what about future work? I think that there are tons more asymptotic equivalences that we could prove. Obviously, I want to prove this conjecture that I proposed, and I have some ideas of how to do that. Pratik and I are going to be working soon on generalized cross-validation using sketching, in which we should be able to show that even if you do sketching, this actually doesn't change anything about cross-validation or generalized cross-validation in particular, which is a super fast way to do cross-validation in large dimensions. I think you could extend this to general linear models, at least to the analysis of the Hessian matrix, because some people have shown how to do that type of analysis using a leave one dimension out approach, because you only have to leave out the dimension of the coefficients that you've learned. And I also think there are really cool asymptotics of PCA that I have started to look into that you can do with this formalism. So thanks everyone who's here and on Zoom for being part of my journey. And I'm happy to take any questions.
Time for questions.
Vishwa.
The last I was excited looking at such result was my advisor's course on compressor sensing. So really, really cool. I have a couple of questions. The first one is actually from compressor sensing. There is this weird phenomenon in compressor sensing called noise folding. It essentially says that if there is a signal dependent noise, the more you compress your measurements, the worse the result becomes. So my way of understanding this and noise folding is that the regularization essentially reduces as you reduce the number of measurements. Does it feel a little counterintuitive, or would you say that they're not related at all?
And if you
So I will
please
repeat this. Yeah, I will repeat this question for Zoom. So the question is about noise folding in signal processing, where if we do a random projection, we lose tons of information, essentially. And how come you're saying that we get more regularization? Usually, if losing information, it seems like things become unstable. That should be like less regularization. And so the answer to this is the inflation factor. So if you see these plots, as we get alpha close to this boundary of what is possible to achieve a certain level of target regularization mu. As we go down on this plot, we actually are blowing up to infinity. So we have, so even though the bias or the expectation in some sense is converging to this highly regularized thing, we have tons of variance, as it were. So it really does blow up in that way, which is why you want to be away from that boundary. We saw it in the other example as well. Here. So as we got close to the limit of possible alphas that could achieve a given mu, things also blew up. This is log scale, so this is quite bad. Okay.
I have another question.
Sure.
Are there sketches that result in the same regularization as on the sketch? I got the idea that I really thought the gap kind of reduces.
Yeah. I don't think. Okay. So the question was, is there a sketch that is going to give the same as the unsketched version? I don't think there is, unless you're in this magical regime that I've discussed, where you aren't doing ridge and your sketch size is larger than the rank. Otherwise, there's always going to be, because there's always going to be some difference. Thanks. Yeah.
Shall we get some questions from the committee, Ginevra?
Sure. Yeah, so you briefly mentioned something about adaptive sketching, and I'm really interested, obviously, in adaptive subsampling as well. Could you maybe speak just a little bit about how you could possibly extend your results to those settings, or how we could analyze those settings?
Right. So the question is about adaptive sketching. I have two answers to give you because I know what you were talking about. And two, with the adaptive sketching that I showed here is in fact something different. So the adaptive sketching that I showed here, I used this term from the literature. My clicker is very bad. So this adaptive sketching refers to something like this. So we're talking about anisotropic sketching. So in this sense, adaptive means that we're going to adapt the covariance of the sketching operator to the data itself. So we have the corollary where we say, well, what if I use sketching with some anisotropic covariance rather than using IID sketching? And so let's say we had some W, then we're going to get the same kind of form, but instead of A plus mu I, we're going to have A plus W inverse. And so the adaptive sketching that we showed on that slide is a proposal to do sketching by using W equals A itself. So we have this A plus mu A inverse, and it's pretty weird stuff, but since I saw it in the literature, I figured I would include it in the paper. So what you're talking about is adaptive sketching in the sense that we'll do something, and then we'll fix some choice of sketching, and then we will perform another step of an optimization algorithm, perhaps, and then maybe we'll choose some different sketching. All right. I believe this is what you're talking about, since we've talked about this before. Is that correct?
Yes, that's correct.
Okay. And so I think that we would use this result to show something about that. So, and the connection here would be, now that we can do what we call generalized ridge regression, we can do iteratively reweighted least squares, which is related to my adaptive dropout paper that we talked about before, that I mentioned at the beginning of my talk, and which of course I've talked about with you. I think that would be how you would achieve adaptivity, is you would, whatever your goal is, say your goal is sparsity, well, you can implement sparsity using iteratively reweighted least squares, which you can implement using an adaptive sketch or an anisotropic sketch. I think that's the best answer I have for you at the moment.
Cool, thank you. Yep.
think there's Anshu and Ben and probably Francis will have a question. You want to go, Anshu?
I mean, Ben, you can go. I can ask even in the committee meeting. Like so. I mean,
Sure. So first of all, Daniel, this was awesome. Thank you so much. So as far as, yeah, I like this work because at least in the problems where I work on, people often sketch or sample because they want to reduce computation, and they regularize because they want to improve the validation performance. And usually when we're giving up, usually the trade-off is that we give up some performance in order to get some computation. But here it seems like, at least if you're okay with the weak guarantee for a single learner, you're kind of getting both, right?
Yeah, that's
which is awesome, right? I like this quite a bit. So my question is a little bit practically focused, and that is this. Let's say that I am okay with having this weaker guarantee for single learner.
Yeah.
It seems like there are a variety of different sketching and sampling kinds of transforms that I can apply to attain a desired regularization. Is there a way to select the combination of these parameters that gives me the most computationally efficient algorithm?
Yeah, first of all, I have a recommendation, which is the subsampled randomized Hadamard transform, or possibly a subsampled randomized Fourier transform, which I think would have this like 2 to the power, a power of 2 problem. Since the problem is the Hadamard transform is only defined for powers of 2, but you could do Fourier transform in general. I think that is probably going to just be the best answer, because I don't think you can do better than an orthogonal, like isotropic distribution. But in terms of how to compare them, I would say that most likely what's going to be most interesting is the first and second order equivalences. So you can actually work these out. You can even work them out empirically, even if you don't know what the relationship is. And you can just, I think you can compare them in a principled way, by saying, okay, this is the amount of induced regularization that I'm getting. Assuming our culture is true, right? You can sort of work backwards. What is the relationship between lambda and gamma?
Oh, that's cool.
And do the second order and say, which one is the giving me the guarantees that I am most comfortable with.
Okay. Yeah, that answers that for me. Thanks.
Yeah, thanks for the question.
all right. So again, like thanks again. Like I mean, as Ben mentioned, there is a lot of cool results that can come out of this. I mean, it's the duality between sketching and regularization, and obviously sketching is done for efficiency. Is great. What I am thinking about is like, obviously, can we 2 things. One is these are results mostly in the linear setting, right? And the non-linear setting where people are interested is in deep learning, where the world is like completely different. More data is better, obviously, and regularization is not good, right? I mean, there's a lot of debate about if you have more data, then you should never be regularizing. But what I would love to see is like, is there some empirical? So let's say you have a sketching method and there is a corresponding, let's say, regularizer that you can come up with. Let's try to do the same thing for a deep learning method and see how much they agree and how much they don't agree, right? I mean, obviously one is rich, but then you can imagine other kind of regularization on, you can just solve it using whatever iterative or whatever way and see how equivalence the results look like with sketching versus the regularization, and see if we can say something there too, because that would be amazing to extend some of these results to even in the deeper setting. So because sketching and deep learning goes naturally together now, and that's the way forward in deep learning because it's too expensive. A lot of things are too expensive there.
Right. Thanks for the question. Can you clarify maybe when you asked this, what do you think sketching in deep learning looks like? Like how does sketching appear?
So basically your results say if you do this form of sketching, it is this form of regularization, right?
And sketching the data.
Can we verify some of those results and see how they behave even in the deep learning setting, right? To some extent.
Right.
And see if there is an equivalence, if there is an empirical equivalence, and if there is an empirical equivalence, or maybe not, right? Then we can figure out what is like. So I'm thinking more on terms of how do you extend this to the next level?
Yeah, the reason why I asked is because I talked recently with Aditya from your lab about some work you guys have been doing where you do essentially sketching of parameters of neural networks, which I think is probably more related to this work than if you were to sketch the input. I think neural networks are probably, at least in the regime that we use them in, like imaging or image classification and things like that. I don't know if sketching the input it makes as much sense there, but I think sketching the parameters is a lot more interesting. And I guess this would have been a better answer 5 years ago than it is now. It's kind of a cop-out answer to say, I think you could do some interesting stuff with the neural tangent kernel. Using sketching on the parameters level of deep neural networks. I don't have a better answer than that, unfortunately.
By the way, another just a quick comment on that. I mean, I know we do sketching on input when it makes sense and sketching on parameter when it makes sense. I haven't seen much difference though. Believe me, whatever we do for parameters, if we do for inputs and vice versa, I know that kind of works. So it's basically just, you know, like you're thinking of two operations, like either you think of parameter as the data or data as a parameter, right? And I have published a number of works switching those two. So whatever result applies for one generally also tends to apply for other, obviously with caveats and things. But that's also another interesting thought, as you could apply the same thing, because if I remember correctly, adding noise, like this is 80's Christopher Bishop's book. If you apply noise to parameters, you get ridge regularization, right? Gaussian noise to parameters to ridge. So sketching the data, there is noise in the data, which is also regularization. Sketching the parameter, there is noise in parameters, which is also the regularization. And maybe that's another direction you can extend this result to, is can we show similar things if we do it on parameter space too?
Yeah, if you're interested in talking more, we should definitely talk further. I think it's less clear to me what to do exactly, just because of the depth of a neural network, what to do with input level sketching. But like I said, I think there may be a path forward for parameter sketching in terms of neural tangent kernel, just because then things become linear.
Okay, yeah, makes sense.
I think we had a question from Francis.
Yeah. So congratulations for the very nice talk and very, very interesting. So a new set of results I was not aware of. So follow up on the questions from the previous person. I think I wouldn't go as far as deep learning. I would start with like random Fourier features, which is just like one even earlier than NTK.
Yeah.
Could you extend this to random Fourier features? Because it seems that the isotropic equivalence and other tools that you have probably can be extended to that case as well if you have uniform distributions on the circle. Have you thought of that?
Yes, I think so. And Pratik and I talked about that some months ago, and then we got sidetracked working on this stuff. I think that we could, and this would be what we would leverage in that case is these so-called Gaussian equivalences or Pennington-Wara distribution, where you can show that if you have some random projection followed by a nonlinearity, this is equivalent in a very precise sense, like even more than this first order equivalence, to just a product of Gaussian IAD matrices plus another IAD matrix. And so given that, since this is a very, very precise equivalence, we could then sketch that matrix. And I think that this would follow very naturally for shallow nonlinear models, like you said, like random Fourier features and things like that.
Sure, but the NTK cannot account for deep networks anyway. So as you say kernel, you're just like, you're not going to be any deep and never better than a random feature kernel up to a small factor.
But the problem is that this type of analysis, like this Gaussian equivalences, is still also just a kernel, because it doesn't allow you to learn the weights.
I agree. I'm all for like learning the features, but at least you will go from linear regression to non-linear regression. So at least you would like, and also you could exhibit the behavior with fixed dimension. Okay, so what what I don't like so much in those random matrix theory
Exactly.
analysis is that you end up imposing some form of isotropy in high dimensions, which is never true. Okay, so
I actually agree here, and I think this is actually a problem with the state of results in this area that I have been concerned about. Like, say you want to do machine learning in very low dimensions, like 2 or 3,
Mhm.
then exactly like you said, none of this random matrix theory, none of this convex Gaussian min-max theorem stuff, like most of it is really not that insightful, because most of the results, like this Gaussian equivalence of nonlinearities, are concentration of measure things that happen at both the input and output dimensions go to infinity. So if you have an input dimension that's finite, most of these tools just don't work. And I think that's actually a huge open question for the field.
Yeah, I agree. Okay, and then maybe like a last question. So you're getting closer and closer to statistical physics in terms
Yes.
of tools and assumptions. So are you planning to go to make the equivalence like stronger, or using their tools? I guess the Gaussian equivalence is used a lot in their papers as well. Can you leverage the thing that they are doing in your case?
I haven't looked into it super closely. To me, at this point, they still feel a bit different, so I'm not sure how compatible or analogous they are. If they are very similar, then of course, I'd love to unify them. I mean, that's pretty much my favorite thing, is unifying things. So,
But didn't you do some form of AMP during your PhD for internship, or
sorry, can you repeat the question?
did you do like approximate message passing at one point during your PhD, or?
Yes.
You could maybe talk about that.
Yeah. Wow. So you don't need to see this. This is PCA. But yeah, so I had proposed during my proposal to study this general linear models with AMP.
Yeah.
Even with as much as I have dug into AMP, this still feels very different from the equivalence that I shown today.
Sure.
So it's not clear to me how they are compatible. But yeah, so what happened with that? Well, over the summer, I realized that the paper that I was trying to base this on had an unfortunate technical issue. I don't think it's a problem with AMP in general, but it made it so that I couldn't cite that paper, and then fixing the paper would probably be months of work.
Okay.
And then I had a melanoma issue, and I just sort of forgot about it and decided it wasn't worth my time for the PhD, and moved on to other things. But yeah, you're right. So like I said, even with as much as I have looked into AMP, which is probably 2 years of staring at AMP, it's not really clear to me that it's the same as the equivalence I showed today.
Okay. No, thanks. Makes sense. Thanks for the comments, and no, I'm done for the questions.
Okay, thank you, Francis. Rich.
Talk a bit about your thoughts for SVD
Oh, PCA.
or PCA. Yeah.
Yes, so this is actually all true that I've shown here. So I kind of have proven it already, but there's just a lot of things I don't understand about it. So let's say we have X, which is some random matrix, and we have its sample covariance matrix. And we want to compute the PCA. So we're going to pi sub A is the projection operator of the principal eigenspace corresponding to a set of eigenvalues A. So usually we would choose A to be like the K largest eigenvalues or something like this, in which case we'd have K dimensional PCA. But mathematically, it doesn't make a difference which set of eigenvalues you choose. So then what we can show is that there's going to exist a family of measures parameterized by sigma squared, where all sigma squared greater than or equals 0, such that for any subset of the non-negative reals, which is your eigenvalues, the projection operator of the principal eigenspace is asymptotically equivalent to some u lambda u transpose. Well, what's u? Okay, u is from the eigenvalue decomposition of the population covariance, which all that's going to change is the lambda. So what are the values on the diagonal? And those values on the diagonal will be this family of measures evaluated on the set A. So whatever mass is on A, so these will be between 0 and 1. What does that actually mean? Well, for example, say you're in, I don't have a picture to show you here, but say you're in a, I don't want to call it spike slab distribution, but say you're in a bulk and slab distribution where you have data generated on a subspace, and then you add noise to it. So it has a relatively few large eigenvalues and a bunch of small eigenvalues is what we're sketching. Then what this tells us is that the projection operator will have two distinct eigenvalues. And they will just be almost 1 on the bulk and almost 0 on the bottom. And the sum of those eigenvalues is always going to be equal to the dimension of the PCA. So I think this is interesting. Like I said, there's a lot of things I don't know about this. I don't know anything about these measures. I just know they exist. And I only know how to compute them via like Cauchy integration, which is not ideal. I don't know if there is anything you can do that's better.
Right. Any last question? Committee or audience? Okay, well, let's thank Daniel. And do Francis or Anshu or Ginevra, do you have any private questions you want to ask? I presume none. So if not, then what we'll do is we will excuse the audience and Daniel. You can stop the recording.
Yep.